Hello student, myself Melissa and today we start with our subject structural analysis part 1 and again we continue with our topic, our chapter thin cylinder. Okay, and again in today's session we try to complete our theory portions. Now first in today's session we derive change in volume for thin cylinder. In previous session we complete direct stresses like longitudinal stress, and second is our hoop stress, and strain like hoop strain and longitudinal strain. Now in today's session we start with our change in volume for thin cylinder. Now first of all here we find change in volume. Okay, so that what is change in volume? Before starting this derivation, what is change in volume? Change in volume, notation of this change in volume is equal to del V, and it is the difference between final volume minus our original volume. Okay, change in volume is the difference between final volume minus original volume. Now original volume V for thin cylinder is equal to area into length. Volume, what is the equation of volume for thin cylinder? That is area into length. Okay, now area of thin cylinder is equal to pi by 4 d square and into length. This is the original volume for thin cylinder. Now next we find out final volume, that means final area of our cross section of thin cylinder and our final length. In original means area into length, that is pi by 4 d square L. Now we find out final volume, and this final volume is equal to final area of cross section into our final length. Okay, now what is the final area? Final area means add the change in diameter also. Okay, because ultimate the final volume is equal to addition of change in diameter, change in length. Okay, so that pi by 4 is as it is, and here d plus del d square, this is the area. Now length, final length, that means L plus delta L. Okay, now again expand this term, pi by 4 in first term d square, this is the expansion of mathematical term a plus b square. Okay, in bracket a plus b square. Now d square and del d square, okay, and 2d del d into this second term L plus delta L. Now next one by one we multiply this first term with L and again this first term with delta L. Okay, now again pi by 4 d square, first term is L, okay, second our del d square into L, then 2d del d into L. My multiplication of this first term with this first value L is complete. Now I multiply this first term with delta L. Okay, now pi by 4 is common, d square into delta L. Look at this, d square into delta L. Second del d square into delta L. Okay, this is our second term, and third term 2d del d into delta L. Clear? Okay, my multiplication of this final area with final length is complete. Now neglecting the smaller quantity like del d square L, del d square delta L, 2d del d delta L. Okay, now why we neglect this smaller term? Okay, if someone say to square of 0.1, that means 0.1 square, the value will be decrease or increase. Simply if we make a square of decimal value, our value will be decrease. So that here del D, del L are the small dimension in thin cylinder. If we here make a square of these smaller values or we make a cube of this smaller value, ultimate our values are decreasing. So that for derivation purpose we can neglect this type of smaller terms. Okay, so simply here the term where smaller dimension are given like del d square, del L square, okay, simply neglect this term. Okay, ultimate our final volume is equal to pi by 4 d square L plus 2L d del d plus d square delta L. Okay, this is my final volume for thin cylinder. Now ultimate our goal is find out change in volume. What is change in volume? Change in volume is equal to final volume minus our original volume. This is the first step of derivation that we already just learned it. Okay. Change in volume is equal to final volume minus original volume. Now what is final volume? Pi by 4 d square L 2L d del d plus d square delta L minus pi by 4 d square L. Now one by one look at this. Pi by 4 d square L, this first term is cancelled. Remaining term is pi by 4 is common for all term. Okay, pi by 4 is separate out. Now first term is cancelled out. Now the second term 2LD del D remaining. In third term d square delta L is also remaining. Okay. Now next del V by divide by V, that means this is volumetric strain. This del V is divided by volume. Ultimate this term is converted into the volumetric strain. Now pi by 4, our answer is pi by 4 d square into delta L 2d delta d into L, and original volume is equal to pi by 4 d square L. One by one divide the term. Okay. Now first term pi by 4, first term divide, then second term divide. Look at this. This pi by 4 are cancelled. D square is cancelled and first term is left with delta L by L. Okay. Look at this delta L by L. Plus again this pi by 4 is cancelled, and second term this d cancel and this L cancel. Ultimate the term this is left 2 del d by d. Okay, write down 2 del d by d. Okay guys, if you remember what is del L by L, that is longitudinal strain. What is del d by d? That is our hoop strain. Okay, epsilon 1 is equal to del d by d hoop strain, and epsilon 2 is equal to our del L by L. Now put this strain in replace of this del L by L and del D by D. Change in volume divided by volume, that means our volumetric strain is equal to epsilon 2 plus 2 times epsilon 1. Okay, this is a volumetric strain. If in data ask find out change in volume, simply cross multiply here volume into longitudinal strain plus 2 times hoop strain is known as our change in volume. Okay, here our theory of change in volume for thin cylinder is complete. Now we go for spherical vessel. Okay, spherical vessel later on. First of all we find out maximum shear stress. Okay, in maximum shear stress, for find out value of this maximum shear stress, it is depend upon two stresses. First stress is our hoop stress and second stress is our longitudinal stress. Okay, maximum shear stress, notation of this maximum shear stress is equal to tau max, and this tau max is equal to difference between hoop stress minus longitudinal stress divided by 2. In calculation we can take this equation directly also, and if someone go with this equation then again is okay. Okay, sigma c is equal to pd by 2t and sigma l is equal to pd by 4t divided by 2. Now ultimate here common tau max is equal to pd by 80. That means there are two equations to solve the shear stress, maximum shear stress. This is the first, sigma c minus sigma l by 2, and this is the second equation, tau max is equal to pd by 80. Okay, this is the maximum shear stress to find out in thin cylinder. Okay, now here we find out efficiency of joint. Okay, in thin cylinder there are two type of joint. First joint is our hoop joint and second joint is our longitudinal joint. Okay, second name of hoop joint is equal to circumferential joint. Okay, now to find out value of this efficiency of joint, here first efficiency is equal to eta L, that means this is the efficiency of longitudinal joint. Eta L is the notation of efficiency of longitudinal joint, and eta C is equal to efficiency of circumferential joint. Now circumferential stress is given by, okay, now if in data find out the efficiency of joint with respect to this efficiency of joint, we find out stresses. At that time we use this equation. Okay, here sigma c is equal to PD by 2T. When we find out hoop stress, we use efficiency of longitudinal joint because these stresses are perpendicular to each other. Hoop stress are act along the circumference and longitudinal stress are along the length. That means ultimately these both stresses are perpendicular to each other. So that if we find out value of hoop stress, we use efficiency of ethyl. Next, longitudinal stress is given by sigma L is equal to PD by 4T eta C. If we want to find out sigma L, then we take efficiency of eta C. Okay, here. Okay, now next we understand the topic thin spherical cell. First of all, we understand what is thin cylinder, how stresses is act on thin cylinder, which dimensions are matter in thin cylinder, and find change in dimension like change in diameter, change in length and change in volume. Now next we understand what is spherical cell and which parameters, which stresses are act in spherical cell, then dimension change of spherical cell, find out stresses. Okay, now here I take two figure. Look at this. In this first figure, this vessel is spherical cell because it is figure of this cell is just like sphere. Again, this is also a spherical cell. Okay, now why we use this spherical cell? Okay, in this purpose of this spherical cell, here in this vessel we store gases or liquid at some defined pressure with matter of factor of safety. That means these spherical vessels are used to storage purpose of air and also liquid. What we can say that this liquid is in form of fuel, but storage of this gases and this fuel will be some specified pressure with defined safety factor. Okay, this is the purpose of spherical vessel. Okay, now first of all we find out stress act in spherical cell. Okay guys, in sphere only one dimension is matter, that is diameter. In thin cylinder there are two dimensions, first is diameter and second is length. So in thin cylinder we find out two stresses, first hoop stress and second longitudinal stress. But in spherical cell only one dimension, that is diameter. This is the half of the section of sphere. Okay, full section is sphere is like ball, and just I cut the section from x-axis. Okay, and this is the section of sphere, what we can say spherical vessel. Okay, this is the thickness and this is internal pressure of fluid or oil, and this is the stress. This stress is act on surface, on circumference of spherical vessel. Now one by one find out the stress that is act in sphere. Okay, for that first we understand the term that is used in derivation. First is our P, internal diameter, P is equal to our internal pressure, and D is equal to our internal diameter. This internal is our internal diameter, and T is equal to thickness of spherical vessel, and sigma is equal to stress induced in spherical vessel. Now first of all we find out total force that is act. Okay, total force that is act in spherical vessel. Now internal pressure P is equal to force divided by area. If we find out total force, then simply pressure multiply with area. Now P is equal to our pressure and area of this sphere is equal to pi by 4 d square. Okay, here we get the value of total force that is act inside the sphere. Now resisting section, again in this sphere, in this spherical vessel, resisting area is equal to circumference of our sphere, and that is pi d, and also multiply with our thickness. Now next, stresses in cell, that means our sigma. Sigma is equal to total force divided by resisting area. We find out total force also and resisting area also. Okay, now P is equal to our area pi by 4 d square P and divide by this pi dt. This is our resisting area. Okay, now next, sigma, if we divide numerator and denominator, answer is equal to PD by 40. In spherical vessel only one stress is act and this stress is equal to PD by 40 because only one dimension are there. Now in second, we find out change in diameter and volume of thin spherical cell due to internal pressure. First of all, we find out change in diameter, then we find out volume. Okay, for that again explain this term. P d is equal to internal diameter, P is equal to internal pressure, T is equal to thickness of cell, and sigma, that is stress in cell material. Now sigma is equal to PD by 40, that we find just now, we find it. Okay, now here we write down strain induced in spherical vessel. Only one dimension are in sphere, that means strain is depend on this dimension and that is diameter. Now strain is equal to change in dimension divided by original dimension. Here one dimension, that is diameter, change in diameter divided by diameter. Now equation of this strain is equal to sigma by E minus sigma by E into 1 by m. 1 by m is equal to our Poisson's ratio. In replace of this 1 by m, we can write also mu. Mu and 1 by m is equal to our Poisson's ratio. Now put the value of this sigma, that is PD by 40. PD by 40E minus PD by 40E, and this is m. Common the term PD by 40E, first term and second term common the value, and 1 minus 1 by m. Okay, this is the equation of strain for spherical vessel. Okay, now next, find out change in volume of thin spherical cell due to internal pressure. Again here we find out change in volume, and this change in volume is depend upon final volume and original volume. First of all, again this is the given data, same, d internal diameter, P is equal to internal pressure, T is equal to thickness, and sigma is equal to stress. Okay, this is the common parameters that is used in derivation for thin spherical cell. Now change in volume is equal to final volume minus our original volume. Okay, so first of all we know the original volume of this spherical vessel, and then after we find final, and difference between this final and original is our change in volume. Now one by one, original volume of spherical vessel is equal to pi by 6 d cube. Okay, here we derive the derivation in term of diameter, so in replace of radius here I use diameter, and that is pi by 6 d cube. Okay, now final volume is equal to our original volume plus change in volume, that means V plus del V, 1 by 1 pi, and in this d we add del d, change in diameter, cube divided by 6. Okay, next, volumetric strain is equal to del V by V. If we divide this volume, change in volume divided by V, ultimately we get volumetric strain, and this volumetric strain final volume minus original volume divided by original volume. Simply put the value, first pi by 6 d plus del d cube minus pi by 6 d cube divided by pi by 6 d cube. Now expand this first term, pi by 6 is equal to, now common pi by 6, neglect this term, expand this d plus del d cube is equal to d cube plus del d cube, then second 3d square del d plus 3 del d square d and minus this d cube. Okay, and divide by this d cube, 1 by 1 cancel out this term. Okay, and del d cube is neglect this term because it is a minor term. Okay, and ultimate, again this is del d cube, cancel this term, and this minus d cube are cancelled. Simply this term are left. Okay, now d square by d cube, that means d 3 del d by d are left here. Okay, now next, here del v by v is equal to 3 pd 4 te 1 minus 1 by m is left. Now del v is equal to multiply with, because equation is equal to 3 del d by d, and del d by d is equal to our volume, del d by d is equal to our strain, and we already find out the equation of strain, that is pd by 4 te 1 minus 1 by m. Okay, now finally we find out change in volume, and for change in volume we multiply this v, cross multiply. Okay, 3 pd by 4 te 1 minus 1 by m into volume. Now what is the volume of this spherical vessel? That is pi by 6 d cube. Okay, right here 3 pd by 4 te 1 minus 1 by m and pi by 6 d cube. Simple. Look at this. Here p and 3 to the 6 and pi by 8, then p common, d raised to 4. Okay, here our final derivation of change in volume for spherical vessel is pi by 8 p d raised to 4 8 te 1 minus 1 by m. This is the change in volume for spherical vessel. Okay, our theory portion is complete now, and next we solve the examples. Okay, just now our theory portion of thin cylinder and spherical vessel is complete. Okay, next we start with our examples. Okay.